Okay, so let's do a little bit of recording. First, when we look at 5.5, we're going to do some problems. We see that the log of a product is the sum of the logs. The log of a quotient is the difference of logs. And if you have a power, you can pull it out front of a log. Here, the idea was to expand this or write it as a sum or difference of the natural log of x, the natural log of y, and the natural log of z. So that means at the very end, what we'd like to see is some number times the natural log of x plus some number times the natural log of y, and then natural log of z. So first thing you do on all of these, hint, we want to work outside in when expanding. So you work outside in when you're expanding. That would be my big hint for problems like these. So I'm going to work outside in. That means here I can rewrite this fourth root as stuff to the 1/4, but then everything to the 1/4 means the top is to the 1/4, so I get this, and the bottom is to the 1/4, so I get 5/4 and 1/4 on the bottom. Well, then the natural log of a quotient is the difference of two logs. Then here's something you need to be very, very careful about. Be very, very careful. Notice I'm subtracting all of this. So I'm subtracting everything in here. I need to make sure and put parentheses around it so that when I break this apart as a sum, I take away both pieces, not just the first one. So the natural log of a product is the sum of two logs. But then we end up distributing that negative to here and to here. And we also pull down that 5/4 up front and this 1/4 up front here. And this is what we have. But then that 7 we can also pull up front and we end up getting this. So now we've taken the original thing and expanded it or rewritten it as a sum or difference of the natural log of x, y, and z. Here we're wanting to condense, yes? And so when we are wanting to condense this thing, remember the other hint that we said is that when you're expanding, the last thing you pull down is exponents. But when we are condensing, that's going to be the first thing you do is pull in all those exponents. So here I have 2 times this. That means I can bring that 2 up here as a parentheses to square everything inside the log. This 3 comes inside and it cubes everything inside of the log. Then distributing, notice in a sense, I'm distributing this exponent over multiplication. It's the idea that a times b squared is just a squared times b squared. So this squared and this squared gives me that. Then if I have x over y cubed, that's x cubed over y cubed. So then I'm now going to view this as one big piece right here in green. And it turns out that the difference of two logs is just the log of a quotient, right? But then again, we have the difference of these two logs turns out to be the log of a quotient. But you have to be careful when you're dividing by a fraction. That's the same as multiplying by the reciprocal of that fraction. So it's really just the log of all this stuff. When we simplify this, we get that. Simplify it further, we get that. Cool. 15, again, the idea of condensing into a single log. First, this 1/3 can come up as an exponent. If you have a times b to a power, that's the same thing as a to a power b to a power. Notice that that only works for multiplying. It does not, and dividing. It does not work for addition and subtraction. So distributing this, we get that. And then we view these. This sum of two logs is just a product, a log of a product. And then we view this difference of two logs as the log of a quotient. When you simplify, you get this. All right, 19. Again, if we're going to solve this sucker, first thing we're going to do, so this may be something that we really need to focus in on that we didn't see as much in class. So when I have this, the idea is that if I have, here's the big idea, note, if you have the log of A is equal to the log of B, then you can say that A is equal to B. That is because log is 1 to 1. The log of x is 1 to 1, that function. So if you have equal outputs, you must have had equal inputs. That's because log is 1 to 1. That's why you can now use this property. So I'd like to get it into a log equals a log, so I must first bring up this exponent, bring up this exponent. And so now I have the log of something is equal to the log of something else. So those things must have been equal. So equal outputs gives you equal inputs. So x squared is equal to 125 or 5 cubed. That means x is equal to plus or minus the square root of 125. But we know that when we plug in here, only positive things can go in. So it's only that one. So big key fact. The log of A equals log of B means that A and B must be equal. That is an easy log equation to solve. So then we go up here, and it kind of looks similar, but the thing that we need to note here is that if you have log base B of y is equal to x, if I can get it into that form, remember that that's a log form, I can rewrite it. It's log form. I could rewrite it if I wanted to in exponential form, which would be that b to the x is equal to y. So here it's not yet in log form because I have too many logs, but this sum of two logs is just the log of a product. So now it's in log form. Notice there's a 1 understood out front. So 2 to the third equals this stuff. Yeah. So that's going from log form to exponential form. And then we multiply this out. We know that we want to get everything set equal to 0 because that's how we can factor. We get two answers, but notice that -8 doesn't work because if you try and plug it back into the original, it gives you garbage. All right, so here they wanted to think about what this looks like. Well, if I just draw a log of x, it looks like this, because I know when you plug in 1, that the log base 3 of 1 is 0, because 3 to the 0 is 1. And we know that log base 3 of 3 is 1, because 3 to the 1 is 3. So I know I've got these 2 points and a vertical asymptote at x is equal to 0. So if I multiply all the inputs by 3, it does the opposite of what I think when I mess with x. So if stretching, it's a horizontal compression by a factor of 1/3. So now instead of at 1 getting 0, at 1/3 we get 0. Instead of at 3 getting 1, at 1 we get 1. So it goes through all these outputs faster as it walks away from 0. 3 times as fast. Okay, and we spoke about this one in class. So if you've got the log base 2 of something and you have the point 1,3 on your graph, then that means we took log base 2 of something where I plugged in 1 gave me 3. So that means 2 to the third is something involving 1. So in other words, 8 is something involving 1. That something involving 1 must have been 8 times 1. So that means that this thing up here must have been x, right? So this would be the function that makes this thing. All right. 5.6. So how would I solve something like this? I would just take the natural log of both sides. And that works because natural log of x is a function. So in this case, we have, if you allow me to move it this way just a little bit. In this case, we have equal outputs means, oh, okay. So equal inputs means you get equal outputs. So I'm taking this number, plugging it into log, taking the same number and plugging it into log. So we had better get the same things because the natural log is a function. Okay. So hopefully that helps a little bit. So we just take the natural log of both sides and get this. What does that allow us to do? It allows us to take this exponent and pull it down. So we get x times ln 5 is equal to ln 3. Remember, ln 5 and ln 3 are just numbers. When you divide, you get this. So the main idea here is that you can take the natural log of both sides, which allows us to pull down this exponent. Okay. Over here on number 5, if I wanted to do this on my calculator, log base 5 of 12, that's just log of 12 over log of 5, where there's an understood base 10 here, and I can now do it on my calculator pretty easily. So this is the change of bases formula. So the log base a of b is log of b over log of a. Pretty handy. Now, if we have this, it's very similar to what we had before. We could just take the natural log of both sides and get this, which allows us to pull down this exponent and get this. But then that allows us to get negative x is equal to this. In other words, x is equal to negative this stuff. Okay, so that's what you would get if you stopped. But notice we could just take a second and notice that a different way to do it would be to rewrite it like this. But then that means 2 to the x is equal to 1 over 8, which means that that x must have been negative 3. So either of these would be okay, but isn't it nice to know that it's just the number negative 3? Here, taking the natural log of both sides, so that is a key tool. So a key tool, take log of both sides. And again, the reason we can do that is because if this is an input and I plug it into natural log, and this is an input and I plug into log, same outputs mean I must have had same inputs, mean I must have had the same outputs because natural log is a function. So it's got to work that I can do the same thing. When I do that, what does that allow me to do? It allows me to pull this down front and this down front. A very important thing here, you must have these big yellow parentheses right here. If you don't, you'll screw things up. Because then you distribute to get this, and you distribute to get this. Notice here, I'm thinking of natural log of 2 is just a number, which it is, and natural log of 5 is just a number. They're two positive numbers. So now I see that the thing that I would like to solve for is x, and it's right here, and it's right over here. So that means I'm going to move this over to get all the x's on one side, and I move this over so that all the non-x's are on this side. So then I see that I have an x in this term and an x in this term. I can factor it out to the front, and then divide by this number, and I get an answer. Okay, so the thing that we learned there, key tool, taking the log of both sides. All right. This one also super interesting. Same sort of a deal though. Notice it's so similar to what we did before. The two tools that we've seen so far in this section, or at least 5.5 and 5.6, one tool that we saw said if you've got the log of A equal to the log of B, then A must be equal to B, right? Because it's a one-to-one function. The other thing we said that is if A is equal to B, then log of A is equal to log of B, and that's because log is, that's because this is because it's one-to-one, and going this way is because it's a function, okay? So in a sense, I could just do arrows this way. These are always the same thing. But then the other really cool tool was going back and forth between log form in exponential form. So anytime you're solving a log equation, you should either think, okay, here's my three tools. Either this, or taking the log of both sides. So maybe I stop and do that really quick. So to sum up, three tools when solving exponential log equations. Number one, if you have the log of A equal to the log of B, then that means that A is equal to B because log, you can play, just turn the sound down if that's okay. Is that okay? Because log X is 1 to 1. Is that okay, buddy? Yeah, you can do all you want, man. To the other tool I have.
Is it recording your voice?
It is, man. So this is equal to this.
Sorry.
No, there's no sorry, man. Go ahead and play all you want. Because, is that okay, buddy? You can play down here. Yeah, just turn the sound all the way down. I'd love you to play down here. Because log X is a function. And then, oh, and that's really the same thing as taking the log of both sides, right? So that's the same thing as taking the log of both sides. That's number two. And then number three, it says that the log base B, let me kind of make that a little nicer here, resize, make it a little bit, oh, didn't mean to do that. To do this, okay. The last one is that log base B of y is equal to x, means b the x is equal to y, because you're going from log form to exponential form. So notice we're just changing the form in all of these examples. So first thing that we notice is if you have log of A is equal to log of B, you can rewrite A is equal to B. If you have A is equal to B, you can write log A is equal to log B. And if you have log form, you can rewrite it in exponential form. I think that those are the three main tools when we're solving exponential and log equations. So that means when we get to here and I see all this stuff floating around, which tool am I thinking? Well, I've already got logs floating around. So I'm either thinking it's going to be a case where I get a log equal to a log, and I can work back and say the inputs must be equal, or I can go from log form to exponential form. Maybe one of those things, yes? Okay, and so I just try and see what happens. Even if I don't know it helps, I kind of move this over, and now notice what I do when I move this over. Now, at this exact moment, I hope left-hand side becomes a single log. So that's what I'm thinking at this moment. If this can all be one log through a bunch of mysterious work, then I'd be able to take log form and write it in exponential form. Well, let's see if we can get it to be a single log. Well, yes, these, when you're subtracting this, that means it goes under this in a single log. And then when you're subtracting this, it means it also wants to go in the denominator. So that's the quick way to combine those. So now I have the log of this stuff equals 2, but there's an understood right here, base 10. So this is now in log form, and I convert it into exponential form. So now it's an exponential form. And so 10 squared is 100 is equal to this. And now it's, can I solve this equation? Well, 100 is the same as 100 over 1. So I can cross multiply and get this. So this times this. This times this gives me 100x squared minus 400. This is here. So then, if I subtract x squared and add 400, I end up getting that x squared is 404 over 99, In other words, x is either equal to positive or negative that number, but notice it can't be the negative version because then this would bark at me. So it's only the positive version. So we get this, which is approximately 2.02. Okay? So part of solving this problem was knowing, okay, the only tools I have are, if I can get a log equal to a log, then I can say their inputs must have been equal. If I have stuff, I can take the log of both sides. Or if I can get a single log equal to stuff, I can convert it into exponential form. Okay? So let's go back and look at some of these problems through that lens. So here, notice I had stuff equal to stuff. And so I know one thing I could do is take the log of both sides. And again, the reason we do is to pull down an exponent. Same thing here. I take the natural log of both sides because I want to pull down this exponent. Here, same thing. Take the natural log of both sides because we want to pull down the exponent. When we look at that last homework and we had this. So I wish it was, since I've got a log floating around and a number over here, I know it's probably not a log equal to a log. I know it's going to be a case where I take log form and convert it to exponential form. Yeah? Here when I started off, it was log equal log, and I knew if I did some work, I could get it into this form. And that's why we pulled this up. And so if logs are equal, then the inputs must have been equal. Tacit assumption that yes, the bases must be the same. So very cool, man. Now let's see. Now we get to this one. Notice what happens here. This is ugly as poop, right? So this is definitely a case of a problem and not an exercise. So there is no way in Hades that maybe you would have right off the bat known what to do. But we need to get comfortable trying something new when it's not a high stakes test. And so if I multiply both sides by 4x, why would I do that? Well, that's because I hate negative exponents. We just see what happens. And very quickly we notice what happens is I have crap squared over here and then that crap over here. So it starts to look like a quadratic. So another reason we might have known to do this is because we hope to get it in the quadratic form because that's a type of problem I've seen before. I'm taking something I don't know how to do and turning it into something I do know how to do. Okay. So when I move everything over, I get this. And if we let u be equal to 4 to the x, then that means we have stuff squared minus 8 times stuff minus 3 just means we have u squared minus 8u minus 3 is 0. So now I can use my old buddy, the quadratic formula, to solve for u. When I do, I get this, but remember, u was 4 to the x. So, since u is equal to 4 to the x, what we can say is that all this is true. 4 to the x is equal to this stuff, but notice I want to get at that exponent, so I just take the natural log of both sides. That pulls down the exponent, and I can divide, get this ugly number, which is pretty amazing. Okay. But notice it was either a plus or a minus, so I have to do the same thing with a minus, get a natural log, but 4 minus the square root of 19 is going to be negative because the square root of 16 is 4, so that's not going to work. So this is the only answer. So the thing to notice here, this was a problem that was on a homework that was meant to stretch us and see that we can do some really cool stuff. I would not expect to see something like that on an exam. But it's important to do work like that. And you should feel very proud if you understand that. Okay, now if we see something like this, this is log of the log of stuff. Well, the first thing I notice is this is log base 10 of stuff equals 2. So I now notice that this is in log form. So one of my tools is to convert it into exponential form. And when I do, I get this is equal to 10 squared. But again, now I notice that this is just base 10. And so again, this is in log form. And so I could convert it to exponential form, right? Man, my handwriting's getting really great in my old age. Form. And so now we have 10 to the 10 squared. That's just 10 to the 100. And that's your answer. Pretty amazing. All right. We have just a couple left. So x to the square root of log is equal to 10 to the 8th. Well, remember, we have 3 tools. Let me go back and get them. Right, and say, copy. So when I'm solving exponential and log equations, I'm really remembering that I have these 3 tools. If I have a log is equal to a log, I can say the inputs must have been equal. Is that what I have here? Well, no. If I have log form, I can convert it to exponential form. Is this log form? Definitely not. So, hey, look what I have. I have an input equal to an input. If I want to, I can take the log of both sides. Why would I do that? Because I want to pull this stuff down out of the exponent. So if I take the log of both sides, I can now pull this thing down out of the exponent, and it comes down here. I don't know if that's going to make it look any different, but I have to do it to take a step forward and then get some feedback from the world and see if I'm going in the right direction. How do I know I'm going in the right direction? Because then over here on the right, this is log base 10 of 10 to the 8th. That cancels out and just gives me 8. So now I'm like, oh, this might be right. But then over here, I realize I have the square root of log of x times log of x. And so what that really is, boop, boop, boop. Let me do this to make that really clear. What you really have over here is, get white, you have log of x to the 1/2 times log of x to the 1 is equal to 8. And so this to the 1/2 times this to the 1 gives you to the 3/2. But I want to solve this thing, so I want to get into this x. So maybe to get rid of this 3/2, I can raise both sides to the 2/3. When I do, these multiply to give me 1, and this is 8 to the 2/3. Well, remember, 8 to the 2/3 is just 8 to the 1/3, and then square it. Excuse me, or you could square it and then do 1/3, but 1/3 is 2, 2 squared is 4. So now I just have log of x is equal to 4. That's much better than what I started with. Why didn't they just give me this to start with? So now I know there's an understood base 10. So I have 10 to the 4th is equal to x, so x is equal to 10,000. Pretty amazing, yes. Not easy, but I think it's doable once you've seen it. This one, this is a challenge problem. Won't be on the test. Notice it's really similar to what we did before. This one, they wanted us to solve for x in terms of y. So they're saying that when you solve this, you're going to get x equals crap, but the only way to do it is to have y's in it. We say again, this is a challenge problem, and it won't be on the test. So one thing we do is, well, I don't like this 2 in the bottom, so I multiply both sides by 2. So I'm trying to solve for x. Well, what could I do? I don't like this negative exponent, so I'm going to multiply both sides by 10 to the x. And when I do, notice what happens. I end up getting, let me write it that way. What I end up getting over here is this 10 to the x gets squared on the right plus 1. So what I have again is stuff squared plus 1, and over here I have 2y times stuff. So another way to view this is we have 10 to the x gets squared minus 2y 10 to the x plus 1. Yeah, do you see that? Yeah. And so now what we're going to do is we're just going to let u equal 10 to the x. If we let u equal 10 to the x, then we now have u squared minus 2yu plus 1, And we can solve for u using our old buddy, the quadratic formula. Use quadratic formula, beep, beep. And we end up getting this ugly crapola. But remember, u was equal to 10 to the x. So believe it or not, 10 to the x is equal to this garbage. So that means since 10 to the x is equal to this stuff, this is an exponential form. So in log form, it would just be this. Yeah. And now if you want to be even more extra, if you pull out a 4 out of this, the square root of 4 is 2. So this 2 pops out. And then if you factor out a 2 out of the top, it cancels out with the 1 at the bottom. And you just get this. That is a challenge problem. It would nowhere be anywhere near a test. But hopefully you see that this is pretty similar to one that we did earlier where we were trying to get it to be of the quadratic form. All right. Pretty amazing. Okay, so then we come over here, it's applications of these suckers. So if the pH level, if this is what it means to be the pH level, then it just wants you to plug stuff in. So if you have vinegar and this is the input, well, if you take negative log of this input, the negative log of a product is the sum of 2 logs. Just make sure that you have these parentheses when you expand. That's why this is a good question. It reminds you that you must have these parentheses or brackets or braces, whatever, when you expand. So this you can't do anything with, but this, you can pull that out front, and log base 10 of 10 is 1. So you get this. And the rest are very similar. This is one of those, it wants to know if you have a 6% rate, that means R would be equal to 0.06, and it's monthly, that means this would be 12. And it means that we go for 12 months. It wants to know how many years would it take to double. So if I've got a principal, I get 2 times the principal, these are going to cancel out. And so I can now solve for t by noticing that this is an exponential form. So this is in exponential form. I convert it to log form by taking that natural log of both sides. Yeah. So exponential form converts into log form, and then you solve and you get t is equal to natural log of 2, all of that, if that's not clear, divided by that 12 natural log of stuff. So you get about 11 years and 7 months. Cool. And then here, this one should be pretty doable, pretty test worthy. They tell us that, what was it? If this is my function and you have 50 as your output, then how long would it take to get from 100 to 50? In this case, it turns out to be 6.58 minutes. It was another case of equal inputs gives you equal outputs. In other words, you take the log of both sides. So because the natural log of x is a function, right? So wonderful work. If there were, let's just remind ourselves, this one seems pretty doable. This is pretty doable. That's pretty doable. This is a challenge problem and will not be on a test. That's doable, but I do agree it seems difficult, but it's doable. That's doable. That is a challenge problem. It would likely not to be on a test. Okay, I'll just say it. It won't be on a test. But it's really pretty, yeah. Hopefully you learned a lot. Super doable. You can do it. Super doable, as are the rest of them, yes? So all the way through 5, 5, 5, 6. I don't think we would see any graphing, so do not freak out about either one of these. Not test worthy. This, doable. In log graphing anyway, I don't think we'd see any of that. Yeah, and all the rest of these are good. So that really reminds us to come down here. To sum up, these are the main things that we saw. because log is 1 to 1, if you have log equal to log, you can just say the inputs are equal. Because log is a function, you can take the log of both sides. And if you have log form, you can put it into exponential form. Awesome. Have a wonderful day, and I'll talk to you soon.